Sorry for the delay. I have no idea what happened. Okay, so today I would like to get to the bottom of our basic problem, okay, which is essentially, remember, trying to express this function here, okay? The Gibbs energy for a system, okay, as a function of essentially one or more progress variables, indicating a particular independent reaction, okay? A reaction is, you have to think of it as a machine, okay, a little machine, an atom conserving or an element conserving mechanism that will change your composition, okay? So if we can express this as a function of the only independent variable, then we'll be able, as I said, to find the minimum and therefore the equilibrium point. To do this, we saw that essentially we needed to express the partial molar Gibbs energy, okay? Because we can write this exploiting the fact that G is extensive, okay? So this is Euler's theorem. This is the partial molar Gibbs energy, which we define as the chemical potential, okay? And I, okay? So today we're trying to find an expression for this mu, for the partial molar Gibbs energy. Generally speaking, I won't use this really heavy notation, but we can write it maybe once or twice. Mu is a function of temperature, pressure, and all of the extensive quantities, which are the number of moles, okay? And by definition, this is the derivative of G with respect to Ni, okay? So this is for species I, okay? Or, so it could be H2O, it could be O2. And this derivative is, as we said many times, calculated as for temperature and pressure constant and all the other moles constant, except obviously for I, okay? And it's clearly an intensive quantity because we're really dividing here two extensive quantities, okay, G and the number of moles. So let's see if we can find a way of actually expressing this, obviously for our particular system, which is clearly a system or a thermodynamic system of perfect gases, of mixtures of perfect gases. That's what we're going to refer to. We're not going to deal with more complex systems like, for example, liquids or supercritical fluids, real fluids, which are at very high pressure. Okay, we're just dealing with the simplest possible system, which is a system of mixtures of perfect gases. So as an intensive quantity, this is homogeneous of order 0. That means that if we multiply by a factor lambda all the extensive quantities, okay, we can put this out like this, but to the power clearly of 0, okay? So it's homogeneous. Did I say first order? I said homogeneous 0 order, clearly. I don't know if what I said before, but anyway. So extensive quantities are homogeneous first order. Intensive quantities like these are homogeneous 0th order. So whatever happens, if you take twice the system, okay, you always have the same value for the intensive quantity. So T, P, and then all the extensive quantities, okay? In particular, if you think about it, I can choose lambda as any number, any constant. So I could even try to imagine choosing it as 1 over n, where n is the total number of moles, okay? I mean, there's nothing really which keeps me from this, forbids me, and therefore, well, you can actually see that if we do choose it like this, then we can even express the chemical potential as a function of these quantities, which are clearly the mole fractions, okay? And this is what we're going to do for the rest of the course. We're going to express it in terms of mole fractions and not of the extensive quantities. Indeed, okay, if you take the 1 over n out, just like we did with lambda, okay, this will have to go to the power of 0, and therefore these two expressions are completely equivalent, okay? Completely equivalent. So we're going to use the mole fractions, okay? And one expression that we're going to be using is really the differential expression. So we're going to write now the differential of the chemical potential, okay, using this expression here. So all we have to do, because it's a perfect differential, we're going to write the first derivative as a function of the first variable here, which is t, okay, at constant pressure and constant number of moles. We can constant composition. So I'll write x as a vector, meaning that I'm keeping all of the mole fractions constant, times dt. Okay, and oops, sorry. Plus this other derivative with the pressure here, so d mu I by dp, where I'm keeping the temperature and the mole fractions constant, times dp, okay? And then the sum of the d mu I by dxi, okay? So for these other variables here, okay, times dxi, where I'm keeping now constant both the pressure, the temperature, and essentially all of the other mole fractions, but with the exception of I. Why am I writing this big expression, differential expression here? Well, because if I can express these derivatives, okay, somehow, for a perfect gas, or a mixture of perfect gases, I can try and integrate this to get mu, okay? So I want to integrate this as soon as I find an expression for these three derivatives, these three kinds of derivatives, we can integrate and an expression for mu, okay? Now, how do we express these? Well, we go back and remember that for the Gibbs energy, okay, we had written an expression which is something like this, minus SDT plus VDP, okay, and then we had the mu i's dni, okay? That's how we expressed the Gibbs energy, okay, where clearly now this minus n, minus s, the entropy with the minus sign was nothing else but clearly dg by dt, right? Constant pressure and number of moles. This is simply dg by dp, okay, at constant temperature and number of moles, et cetera, et cetera. And this is by definition dg by dni, okay? So how do we proceed? Well, if, let's take this first derivative, if dg by dt, okay, is equal to minus s, okay, then we're interested in this derivative here, okay? So d mu I dt, okay, we can write it in the following way. This is the derivative with respect to temperature of what? Of mu I, right? But mu I, we know by definition, is dg by dni, right? So what we can do here, we can switch the order of integration. Okay? And now derive with respect to the number of moles, what? dg by dt, right? But we just said that dg by dt here is minus s, right? So this is nothing else but ds by dni, okay? At constant pressure, a number of moles. All right, this is I. So long story short, by definition, we defined them last time. These quantities are partial molar quantities. So what this is, in fact, is the partial molar entropy, okay? Exactly like mu is partial molar Gibbs energy, you know, this is the partial molar entropy, which means essentially the change of entropy when you add 1 mole of substance I, okay, to the whole mixture, okay? So this is a partial, I'll write it here. And we can really do something very similar to this quantity here. So again, I really want to express now this term, okay? So remember that, first of all, that dg by dp, at constant temperature and number of moles, is equal to the volume, right? We just saw that. So if we're interested in this derivative here, d mu I by dp, at constant temperature and mole fractions, we again use the definition of mu I, which is dg by dni, the partial molar Gibbs energy. Okay, we switch the order of integration, and we have dg by dp, which we said is equal to the volume, right? And so this is essentially dv by dni, okay, which is equal to, by definition, okay, at constant blah, blah. I mean, I don't want to make it a little too heavy here, the notation, but what this is, by definition, is a partial molar volume, okay? Which is essentially the change of volume when you add 1 mole of substance I to the whole mixture, okay? Which is not necessarily trivial, because remember, it could be that the volume changes differently from when you add 1 mole of I, for example, to the pure species I, okay? In general, this is not true for a perfect gas. We will prove this. So I have expressed, again, these two, remember I wanted to integrate this. Now I have expressed these two quantities. So let me write down now d mu I. I haven't done anything special now. I've just defined what the partial molar entropy is and the partial molar volume. Okay, and this, sorry, this is a plus, and we'll keep this as d mu I by dx I, okay, times dxi. Now, so this is in a way very similar to what we wrote before for the Gibbs energy, right? The Gibbs energy had over here had a minus entropy, volume, and mu I. Now you have essentially partial molar quantities here, okay? Why did we write this? Well, let's, for example, concentrate on the volume, right? So for a perfect gas, now we're specializing our, you can hear me, right? Okay, we will specialize this to a perfect gas now, okay? We're concentrating on a particular thermodynamic system, okay? We know that the volume can be written as R. This is a very bad R, but I mean, it's the universal gas constant, T, N divided by the pressure, right? And, well, for a mixture of NS species, well, N is the summation, right, of the NIs, right, divided by the pressure. Now, think about it now. We can directly now estimate, not estimate, calculate the partial molar volume, VI, because VI is nothing else but the derivative of the volume with respect to Ni, okay? When I'm keeping the temperature constant, the pressure constant, and all the other constants, but Ni. So look at this expression here. RTP, in our case, is a constant, okay? And which multiplies a summation of all the Ni's, okay? Which are all constant. We're all keeping them constant except Ni. So when I'm differentiating with respect to Ni, what I get is essentially RT over P, right? And which is pretty much constant and the same, as you can see, for all species, okay? If I rewrite it in terms of V over N, then you see that and this is quite important, the partial molar volume, the partial molar quantity now is really equal to the molar quantity. So what we were saying the other day, generally this is not true. It won't be true for, for example, the chemical potential. It won't be true for the partial molar entropy, okay? It will be true, however, for the partial molar enthalpy, okay? Now this may be confusing, but think about it. We're mixing, okay, gases here. And, well, if you add 1 mole of one particular species to a mixture of gas, you don't expect this gas to increase its enthalpy, right? To become hotter or decrease it, become colder, right? The same thing here. If you add one mole of species I to a mixture, you don't expect to have an increase in volume which is different from your partial molar volume. Okay, so what this is saying, in fact, is that all partial molar volumes VI for all species are the same. Okay, which, by the way, is Avogadro's law. Okay, which means essentially that the same number, you can see it from here, the same number of the same quantity of different gases, okay, occupies the same volume. Okay, so this also means that adding the single mole of a species I, the pure species I, to a mixture is really identical to adding species I to the pure, okay, species I. So the process of mixing, in some sense, does not cause a defect or excess of volume, okay? And this will be clear later on when we talk, or actually right now when we talk about the process of mixing, okay? So what we say here from this expression is that there is no mixing volume, okay? Whereas, as you will see, indeed, there is a mixing Gibbs energy or mixing chemical potential. So let's use this result, okay? Because now we have everything we need to really determine mu I, okay? Because suppose that I have a system which I keep at a constant temperature and at a constant pressure. Sorry, forget the constant pressure because it's confusing, obviously. I keep the system at a constant temperature and constant, so dT is equal to 0. Okay, so this term is not there. And consider that I'm not changing the overall composition, okay? So the dxi is also equal to 0, okay? So essentially, I'm not changing each mole fraction, okay, for all the species. Then we can express this differential as essentially VI dP, right? Which is equal to RT over P dP, okay? So clearly, we're not considering the system at constant pressure, although this will be a little confusing for you, I'm sure. So how can we use this expression here? I think we should go to this picture here. So this is where our approach of the very first lessons comes in helpful and handy. Because remember what we tried to do at the beginning of the course, okay? We had some sort of system with an internal constraint, and then we were releasing the internal constraint, right? Like a piston or something. Now, really, here we're talking about something very similar. We're talking about essentially creating a mixture, okay? So we're trying to put together, okay, gases of different nature. So what you can see, what you can imagine here is having a system, okay, which is constrained internally by impermeable walls like this, okay, which is dividing the pure species. So, for example, we have species 1 here, species 2 here, and species 3 here, right? Okay. So imagine that each subsystem is at a pressure P, okay? And suppose now that we want to remove these internal constraints, right? We want to remove these impermeable walls, okay? And what we want to do, therefore, is by removing them, we want to expand, okay, each subsystem, okay, at pressure P to its partial pressure P. Because clearly here now, each species is going to be present with a mole fraction, x1, x2, etc. Okay? So what we're doing is we're taking essentially the subsystem of pure species at pressure P, which is equal to pi over x. Remember, by definition, okay? And why are we expanding? Well, clearly because x is less than 0, right? Because clearly the mole fraction here of species I in the mixed system is clearly less than 0, and therefore, by definition, we're dividing something by less than 0. This is clearly bigger than pi, okay? So what we're doing is we're expanding from pressure P to pressure pi, and we're doing it for all species, okay? So we're clearly removing the internal constraint, okay? So suppose that this particular species here was present, for example, with a chemical potential, which was essentially mu1, and then we indicated with the superscript 0, indicating essentially the fact that it's a pure substance, it's not mixed. Well, in the mixed system, the chemical potential of species 1 is going to be something else, for example, so mu, right? And clearly mu1. Clearly mu2 here, mu3, etc. Right? So we have here instead the pure value, okay, with the for the relating to the pure substance. Okay. So I hope it's clear how we're essentially creating a mixture. We're expanding, okay, by essentially removing these internal constraints. We are expanding the subsystem to its final partial pressure. Okay. In the mixed system, okay? So having said this, with this picture in mind, well, then we can use this expression here because we're essentially creating, okay, this mixture by initially having a pure substance, okay, at a total pressure P, okay, bigger than this pressure here. So what I'm doing, I'm taking this and obviously integrating it. So I will have mu I in the final state at the partial pressure pi, okay, here, minus, okay, the pure kind of state at temperature Tp, okay? So here you can remind yourself that this is in the mixture at pressure pi, and this is when species I is pure, okay? In the unmixed system, okay? And what is this? Well, this is nothing else but the integral from the pressure P to the pressure pi, okay, of the partial volume, right? Which is obviously, which is VI dP, okay, which is RT over P dP, okay, which is equal to, RT is a constant, because clearly we're keeping T constant. So this is a natural logarithm of Pi over P. So as you can see, we have now expressed, okay, I'm sorry, it's really ugly. We have expressed the chemical potential in the mixed, okay, system of species I, okay? we can even, well, because pi is p times xi, we could even express it as tp and xi, okay? And, well, this is equal to, well, we'll put this over on the other side. So a pure, okay, chemical potential. So the chemical potential in its pure state, okay, where it's not mixed, okay, plus RT, okay, logarithm of this ratio, pi over p, which is nothing but xi, okay? Obviously, why is this pure? Clearly, I mean, you can see it from here. If xi is equal to 1, okay, then clearly the quantity, this is mu I, the quantity mu I, t, p, and clearly 1 is equal to, you see, this is 0, okay? And we'll have mu I of t, p, okay? Which we can call as essentially mu 0, okay? In its mu 0 I, in its sort of pure form. So, I mean, we can rewrite it as many ways as you want. So the chemical potential at T, P, and Xi, okay, this will be essentially chemical potential of I in the mixture, equals to mu I 0 or naught of Tp and clearly Xi equals 1. And this is the chemical potential of I as its pure, in its pure form, okay? Unmixed. Now, obviously, what this is, okay? Well, this will be what? It will be the variation of chemical potential due to mixing. Okay, I'll write it here. Okay? So in other words, we can write it in short, mu I equals mu I 0 plus this quantity here, which we call delta mix, okay, of mu I, okay? Again, if we want to refer to this, the difference clearly between mu I and mu I 0 is delta mix of mu I, okay? So this is the variation due to mixing. So clearly, mixing changes essentially the chemical potential, okay? I will prove again that it doesn't change, okay, the partial molar volume. We just saw that, okay? So the mixing volume is 0, okay? Which is, as I'll say later on, it's not true for some liquids, for example, okay? But it is true for perfect gases. Now, what does this mean? Well, let's try and see now if we can actually find out what happens to the Gibbs energy, okay? In the process of creating this mixture. Can we do that? Well, if you remember, the Gibbs energy, okay, is nothing else but Ni times mu I, right? So now that we have an expression for mu I, we can write it certainly. In fact, what we can do is we can also write the molar Gibbs energy, which is G divided by the summation of Ni, which is the total number of moles. So it's essentially the Gibbs energy per unit mole, okay? And this, by dividing by N, okay, this will be nothing else but the summation of Ni divided by N, which is Xi times mu I, okay? And this we can write right away as Xi mu 0 plus RT logarithm of Xi, okay? Let's write it in full, okay? So the for a system that undergoes, okay, mixing, the molar Gibbs energy, G, you've noticed that I use the lowercase, okay, because it's a molar quantity, is equal to, well, this quantity here, sorry, this quantity here, okay, plus, well, RT is a constant. I can write it outside of the summation sign, and then Xi logarithm of natural logarithm of Xi. We have two terms here. This is usually called G0, okay, and it's a standard molar Gibbs energy, okay, and it's referred to essentially the pure components, okay, and this is what we call the mixing Gibbs energy, okay? So the mixing, the difference in Gibbs energy through the creation of a mixture from its pure components, right? So G minus G0 is equal to this delta mix, which is essentially Xi logarithm of Xi, okay? Now, we know that Xi, all the Xi are numbers that are smaller than 1, right? Well, if you compute, sorry, there's a summation sign. If you compute these quantities, okay, well, you realize that these are all negative, okay? Because of the fact, intrinsically, the fact that Xi's are less than 1. So really, it's pretty obvious that due to mixing, the variation, okay, of Gibbs energy is negative. So if I keep the pressure and temperature constant, the formation, okay, from its pure components of a mixture of gases decreases the Gibbs potential of the Gibbs energy, the Gibbs energy per unit mole. Does that ring a bell? It means, okay, that the process of mixing is really a spontaneous process, okay? So if I have pure substances, segregated and impermeable, okay, kept pure through impermeable walls, if I remove the internal constraint, there will be clearly a decrease in Gibbs energy due to the fact that this process is clearly spontaneous. And we know this from experience, right? If you have, well, in the room you're sitting in, okay, doesn't separate nitrogen and oxygen of the atmosphere. The atmosphere is composed of a mixture of nitrogen and oxygen, okay? And if I have nitrogen and oxygen separated at first and I remove the impermeable wall, we know for a fact that these will mix spontaneously, okay? And the fact, mathematically, the fact that this is clearly the mixing Gibbs energy is negative means exactly that. In fact, we could even do it with the entropy and see if the entropy actually increases, okay? And, well, if you remember what the partial molar entropy was, it was d mu I by dt at constant pressure and number of moles, okay? And now that we know how to express mu, okay, we can write down mu 0 I plus RT logarithm of xi, okay? So, and this would be this derivative here of the pure species, okay? Plus, we derive this at constant composition, okay? R is a constant, so we have R logarithm of xi, okay? And what we call this, essentially, we will call this, so this is SI, we'll call this minus SI naught or SI zero, meaning that this is the value of the partial molar entropy in the mixture. This is the partial molar entropy of the pure substance, okay? And this is the mixing entropy, R logarithm of xi, okay? So in fact, we should change sign here. Minus R logarithm of xi. So this is with the minus sign is the delta mix, okay, of SI. So very similar to what we did before, these, well, the entropy is an extensive quantity. So for the entropy, we can write down the partial molar quantity times the number of moles, okay? The specific quantity is essentially, well, it's the lowercase s, so this is capital, okay? This is the lowercase. Is nothing else but SI times XI, right? And therefore, we can substitute. So this is SI 0 minus R logarithm of XI. Minus R, summation of xi logarithm of xi, okay? And it is pretty clear that because there's a minus sign here, okay, and this is negative, the mixing, okay, entropy is positive, okay? So mixing causes an increase, okay, in entropy, okay? Which again proves that it is a spontaneous mixing is spontaneous, okay? It's a spontaneous process. Well, what about the partial molar volume? Okay, we did it already. Let me repeat now with this expression. So this is by definition d mu I by dp at constant temperature and number of moles, okay? So we have to derive with respect to pressure, okay? Plus RT logarithm of xi. And as you can see, because this doesn't depend on pressure, it depends only on this. This is essentially only d mu 0 I dp, okay? So what this is essentially the partial molar volume, okay, of species I in the mixture is equal to the partial molar volume in the pure substance, okay? So there is no difference. In fact, Vi minus Vi 0, which is supposed to be the delta mix Vi, okay, is equal to 0, okay? So the mixing volume is 0. So what this means is that mixing causes essentially no change in volume for the perfect mixtures, okay? This is not necessarily true for liquids, okay? There are mixtures, for example, of water and ethanol, okay? And for these, okay, adding, for example, to water, adding some ethanol causes an effective delta mix of volume. It means that I don't have the same number of volume as I would have if I were to add, for example, water to pure water, okay? The same volume, huh? So there is a net sort of different, okay, there's a defect, okay, of volume due to the molecular interaction, because clearly in liquids, the molecular interaction between different molecules can, in effect, cause a defect, okay, also of volume. What about enthalpy? Just to finish this concept. So meaning, does enthalpy change, okay, if I mix at the same temperature, okay? If I mix a species I in a mixture, in other words, if I add a pure species to a mixture, will the enthalpy, the overall, will the mixture heat up or cool? Now, obviously, for perfect gases, this is clearly not the case, right? We can really prove it, and you can prove it by yourselves, but I'll give you the short version. The partial molar enthalpy, you can prove very easily that it's mu I plus TSI. Okay? The partial molar enthalpy of species I is the chemical potential, the partial molar Gibbs energy plus TSI. And you essentially you can prove this from essentially H equals G plus TS. Okay, and the fact that mu I is equal to dG by dNi, et cetera, okay? This would be equal to essentially dH by dNi minus T ds by dNi. And this is clearly HI minus, well, I proved it, okay? So this is what? Well, for the chemical potential is mu I 0 plus a delta mix, okay, mu I. And this would be T multiplying, again, SI 0 plus a delta mix, right, of SI. So let's regroup the pure values here. So this would be my essentially H0 or standard molar enthalpy at of the pure species. plus the two mixing quantities, which is the one relative to the chemical potential, and the other one to the entropy mix. Okay, and this is overall a mixing enthalpy. Okay, so if there is a variation of enthalpy of the system due to the addition of 1 mole of species I, well, if we write down this mixing enthalpy in full, the mixing chemical potential here is what we saw before, RT, logarithm of x, and the mixing entropy is R logarithm of x times t, so minus R logarithm of x, so you see it's exactly the same thing. Okay? So it's 0. So what does that mean? It means that for enthalpy, the mixing enthalpy is clearly 0, so the enthalpy of a system does not change, okay, when on mixing. So at constant pressure and temperature, mixing does not cause any sort of cooling or any heating. So essentially, the partial molar quantity is equal to the molar quantity in pure state plus no mixing. Okay, so essentially, that's why essentially the enthalpy is always considered here as we drop essentially the 0. Okay, because it's automatic, okay, that the enthalpy is essentially, for a perfect gas, is essentially referred to the pure state, okay? So in fact, what we do here all the time, we express the enthalpy of species I, okay, without specifying the fact that it's a pure substance, okay, whether or not in a particular mixture, okay? And because clearly dH is equal to Cp T dt, okay? Cp of species I, if we integrate this, we have some constant which we call the enthalpy of formation, generally at a reference state, okay, a reference temperature, sorry. And then, sorry, plus the integral of between the reference and the temperature T of Cp. So this is the standard enthalpy of formation, this one here, and this is what we call the sensible enthalpy, right? Which I think you've seen many, many times. Wow, I mean, we have now most of the tools that we need, okay, to go back to our original problem. Remember what the problem is? I give you some sort of reaction, okay? How do you express this, okay? How do you express the Gibbs energy as a function of the progress variable? Why did we want to do that? I want to remind you for the 10th time, when I give you a chemical system, it's essentially a mixture, okay, of molecular species, okay? And the only way that we know how to change the composition is through a balanced reaction, an independent reaction, a reaction that conserves atoms, okay, which is that constraint, okay, in the phase space of the composition space. It's a vector in the composition space. How do we move along this vector? Through this variable here, psi, right? So now we know how to change the composition through a chemical reaction. We know how to conserve atoms. We know how to move along this reaction. by moving psi. Now we have to express G, okay? If we know how to express G, then we'll find the minimum, and that's where our system will spontaneously move towards, okay? Let me give you an example, because it's the best way of really expressing this whole thing. So suppose I have another reaction. Let's consider the reaction between hydrogen and nitrogen, okay? Sorry, N2, to give ammonia, NH3. By the way, your future generations will, I think, hear a lot about ammonia. I guess I don't know if I told you, but ammonia is really now becoming a very hot topic because, as you can see, well, first of all, you know that it's liquid at room temperature, so it's quite dense and it's easily transportable through ships, for example. And what you're actually moving when you're moving ammonia, you're moving hydrogen, and a lot of it, okay? Because it sticks to nitrogen. And since the future will be burning hydrogen as opposed to fossil fuels, for obvious reasons that we've discussed, then this is really one of the best, most efficient way of moving around hydrogen around the world, okay? You can't really move hydrogen in liquid form because that would be cryogenic, it would boil off, and you would need a lot of energy to do that. And you can't really move it in gaseous state because it's very, very light and density is very, very low. So you need to probably compress it. But here, okay, this is one of the most efficient. Okay, of course, there's drawbacks. Okay, ammonia is toxic, it's poisonous. Anyway, we have our chemical system composed of H2, N2, and H3. Okay, we have our little composition changing machine, which is essentially our balanced equation, which is our constraint on the phase space, okay? Our reaction, we can move around the reaction by changing psi, okay? So if we also can write this function here, we know how to establish chemical equilibrium, okay? It took us 10 lectures, but we got there, more or less. So let's remind ourselves a little bit of the definitions here. Okay, this is the definition of the progress variable, so that we can write essentially for every species the number of moles. Okay. Let's choose the initial composition. For sake of simplicity, we can choose the initial vector, okay, as essentially the stoichiometric vector, okay? So better still, n0I as n as ni prime I, okay? So essentially, we start from an initial number of moles of H2 equal to 3 divided by 2. The initial number of nitrogen moles is 1 divided by 2, okay? So I'm just writing these two initial, and clearly initially we have 0 numbers of moles of ammonia, okay? This means, if you remember, that psi is automatically changing from 0 to 1, varying from 0 to 1, okay? So now we can really write down an expression for the number of moles. So number of moles of H2 is equal to what? To the initial number of moles, which is 3 divided by 2, plus this quantity here, which is 0 minus 3 divided by 2, okay, times psi. So we can write this as 3/2 of 1 minus psi, okay. For nitrogen, we do the same thing. And we essentially have 1/2 minus 1/2 of psi. It's pretty straightforward. So this is it. And for ammonia, the number of moles is, well, 0 initial plus 1 minus 0. So this is very simply psi, okay? So, well, I mean, we can draw our usual graph, okay? We have psi varying from 0 to 1, okay? We have ammonia here starting from, see, 1/2. Sorry, ammonia. Nitrogen starting from 1/2. And this other guy, hydrogen, is starting from 3/2. So over here. And they I have the same problem now. They linearly go to 0 here. Wow, that was straight. Can you hear me, by the way? I haven't been talking to myself.
Yes, yes.
And so this is hydrogen, and this is nitrogen, right? And this clearly is water. Okay? But not only this, because we can also, remember that we're working on mole fractions. We can also find the mole fractions. How do we do this? Well, we have to divide each of those number of moles by the total number of moles. What's the total number of moles? Well, it's the sum of all the number of moles. So I have to sum this, okay, plus the number of moles of nitrogen, plus the number of moles of water, okay? What do I get? If I haven't made mistakes, minus psi. Okay, so how do we express, for example, the mole fraction of hydrogen? Well, we take the number of moles of hydrogen, we divide it by the number of total number of moles, and we have essentially 3 divided by 2, 1 minus psi divided by 2 minus psi. Okay? So it's a little boring, but we'll get there, hopefully. So for nitrogen, same thing, okay, is 1/2 1 minus psi divided by 2 minus psi, which is the total number of moles. And for ammonia, we have essentially, very simply, psi divided by 2 minus psi. Okay? So what do we do with these, this composition? Well, the usual, okay? What's the Gibbs energy? The Gibbs energy, again and again, is number of moles times the chemical potential, okay? So it's the summation of the number of moles times what we know how to express now. It's mu I naught plus RT logarithm of xi, okay? And now we can express, I hope you realize now, we can express both N as a function of psi and xi as a function of psi. We wrote down the expressions, okay? But let's keep it general, okay? Look, G essentially has two contributions, right? Essentially, it has this contribution here. Okay? And this contribution here. Okay? Well, you will recognize here essentially what? Well, a function that we can call G0, okay? Still a function of, well, we can call it of psi, obviously, which is the standard Gibbs energy, okay, of unmixed components. You see, essentially, these are all in their pure form, okay? And this, by construction, will be nothing but the mixing Gibbs energy, okay? Still a function of psi, okay? So this is the variation of G due to the process of mixing at any psi. So imagine essentially the Gibbs energy, okay, as being for a given composition, okay, the Gibbs energy of the pure substances, okay, so when I have, so to speak, internal constraint that keeps them from mixing, okay, and then this is the change, okay, of Gibbs energy upon mixing, okay, for the same number of moles, okay, so I have these number of moles of pure species separate, and then I mix, okay, and this is the change of Gibbs energy, okay, so that's what in general G is, okay. G is pure components at this composition here. So I have N1 moles of H2, N2 moles of N2, et cetera, but non-mixed. Then I mix them, and this is the change of G. The sum clearly is what your G is, okay, in general, what your Gibbs energy is. And all of those is function as a function of how much far to the right or to the left I'm shifting the composition in the chemical reaction. Okay, so really nothing special. In fact, well, G0, which is this guy here. Okay, for our system, you can write it down as NH2. Mu 0 H2, etc. Okay, and 2 mu 0 and 2 plus number of moles of ammonia NH. Mu 0 NH3. Okay. And that's what we call the standard state Gibbs energy of unmixed components, okay? And then the delta mix will be what? Will be essentially, well, RT, we can put it outside. And then it's the sum of NH2 times the logarithm of XH2, okay? The mole fraction, etc., and 2 logarithm of x and 2 plus, and well, I did the same thing here, h3 logarithm of x and h3. Okay, that's the expression. You would have to substitute all the functions that we found before, but it would be really confusing. Okay. But the nice thing is that now we can really draw this graph. It's an analytical expression. So we can actually draw the graph. Let me give you a few numbers so that we remind ourselves. Well, first of all, I won't do much explanation here, but the standard state chemical potentials of the pure hydrogen and nitrogen is really identically zero. Okay. On the other hand, you can calculate this. I won't get into the details of how you calculate the standard state quantities. Okay, but it's really a matter of defining a reference state. Okay, well, it depends on temperature. Clearly, it is, for example, 4.8 kilojoules per mole at a temperature of 500 Kelvin, and it's decreases to -16 kilojoules per mole, okay, at a temperature of 298 Kelvin at room temperature. Okay, so we'll need this later on. Okay. Because we can write G as a function of, as G0 of the unmixed components plus a delta mix of G, okay? One thing that is going to turn out to be quite important, okay, is this quantity here, what we call delta G0, okay? And what this is essentially the difference between the standard Gibbs energy of the unmixed species, okay? But at psi equals 1, so when your reaction is all shifted towards the right, minus G0 of the, essentially the products, okay? Sorry, of the reactants when the reaction is completely shifted to the left, okay? So what this is the change in standard Gibbs energy of the unmixed, or if you want energy between, not of, between unmixed reactants and unmixed products. Again, I'm sorry for the handwriting, but I'm just trying to do my best, but this is the best I can do. Now, it may not appear completely clear what this means, but you'll see in a second that it can be quite important, especially in the definition of what we will define as the so-called equilibrium constant, okay, in chemical equilibrium. But let's do one thing at a time. So one thing that we can do with this guy here, we can see what happens when psi is equal to, for example, 0, okay? When the reaction is all shifted towards the left, towards the reactants, okay? So G of psi equals 0 is equal to G's, the standard state of the unmixed reactants, G00 plus delta mix G0, okay? So let's see, it has two terms, okay? G0 is essentially what? The summation of the number of moles times the mu 0. So it will be 3 halves mu 0 for hydrogen plus, remember, this is the composition when psi equals 0, a half mu 0 nitrogen, okay, plus 0 moles of ammonia. Because of what we said before, the mu 0 for hydrogen is really 0, and it's also 0 for nitrogen, and this is also 0 because there's a 0 here, okay? So in fact, G00 in this case is 0. And then we have to add the delta mix, right? Which was RT 3/2 logarithm of X of the mole fraction of hydrogen, which is 3 divided by 4. You can, again, I'm adding here, I'm calculating everything for psi equals 0, plus 1/2, this is the number of moles, times the logarithm of the mole fraction, which is 1/4, okay, plus 0, okay? And that's delta mix, G at 0. Okay? So that's psi equals 0. And this, in fact, if you do, if you calculate these numbers here, it would be something like RT, okay, times, and these logarithms add up to essentially minus 1.12, meaning that it's negative, right? Because clearly that delta mix is negative. So again, let me just try and draw it finally, right? So what do we have here? We have essentially psi changing, going from 0 to 1, okay? And I really want to express this function here, right? That was our initial goal. So there will be a 0 here, okay? So let's also draw the 0 level here. Okay. So let's see what happens at psi equals 0. So we just saw this, right? Well, look at this. We calculated the standard Gibbs energy of the unmixed reactants, and it turned out it was 0, right? So here we have essentially unmixed reactants, which is essentially 3 divided by 2 moles of H2 plus 1/2 mole of nitrogen, okay? So that's G0. Let's write it over here. G0 of 0 is equal to 0. So this is where we start. We start from 2 reactants, which are unmixed. Then what do we do? We mix them because, of course, in order for them to react, you have to mix them. And mixing causes a decrease, okay, of Gibbs energy, which is equal to delta mix G, okay, which is, again, 0, okay? So we're over here. In fact, if you do the maths, it will be, well, you have to multiply by RT, okay? So it would be something like 4.6, minus 4.6 kilojoules, okay? And this is clearly the same composition, okay, but mixed. Okay, so this is where we are now. Now, let's see what happens on the other side, at x equals 0, okay? Sorry, x equals 1, okay? not X, sorry, Xi. God, today I'm just thinking something and saying something completely different. So now I want to see what happens when the reaction is all shifted towards the right at Xi equals 1, okay? So again, G of Xi equals 1 will be equal to, well, G0 at 1 plus the delta mix of G at 1, okay? Now, let's see G0. When you have all the reactions shifted towards the right, we don't have any products, right? So we have 0 moles. All right. Again, I did it again. When the reaction is shifted all to the right, you have 0 reactants. You only have products, okay? So 0 reactant of hydrogen, so 0 mu0 H2 plus 0 mu0 nitrogen plus the final mole of clearly ammonia, which is mu0 NH3, right? So this is the value of G01, okay? Which you can now multiply now mu0 of ammonia, sorry, which was 4.8 times 1, so it's 4.8 kilojoules, okay? And clearly now, look, we have a pure species, right? So what about the mixing? Well, it's going to be RT, the mixing G. Well, it's going to be 0, but let's prove it here. Well, we have, again, 0 moles of H2, 0 moles of N2, and then you have essentially 1 mole of ammonia, logarithm of what? Of the mole fraction of ammonia, which is 1. So clearly, we have a pure substance, and therefore the mixing Gibbs energy is, by definition, at Xi equals 1, is by definition 0. So we're left with this guy over here, okay? Essentially, G of 1 is equal to G0 of 1, which is 4.8 kilojoules. Okay? So essentially now, oh, and by the way, if you remember, the difference between the unmixed, or the standard Gibbs energy here, G1 minus G0, okay, is delta G0. This difference here, okay, it's G01 minus G00, okay? Well, now what do I have? I go from this point, there's a function here all the way down connecting this point here, clearly. Okay, so I start from unmixed reactants, I mix them, I get here, then I change the composition through my chemical reaction all the way down to the product, which is only 1, is pure. So this is the value of G. You also have the analytical expression, okay, of G as a function of Psi. And so you'll realize that it's something like, if you actually graph it and draw it, it's something like this, okay? And magically, we finally got to a point where we can draw it. We have defined all these mixing values, okay? Because clearly now you have to mix, okay? You have to, at any time, have a mixture of components of reactants in order to have them react. But most importantly, there is an intermediate point where the Gibbs energy is at a minimum. And this is our value oops, it's our value corresponding to the chemical equilibrium. So this is the equilibrium point, okay? It means that spontaneously, okay, the system will be driven towards this point, either from left to right or from right to left, depending where we start from, okay? And this would be my minimum of Gibbs energy, so dg by dxi equals to 0, okay? But we did all of this purely, totally analytical. Give me just 1 minute, because remember that I gave you the value of mu0 for the reactants and the product at 2 different temperatures. I used here the values at 500 Kelvin. What happens if we do the same, okay, at 298 Kelvin? Well, you still have essentially your 0 level. So this is 0. This is, again, G psi. Again, G0 for the products, sorry, for the reactants doesn't change because they're both, the mu zeros are both 0. You will have now, again, a mixing decrease, okay, a mixing Gibbs energy, okay, decrease of Gibbs energy, okay. This is a temperature 298 Kelvin, okay. So all we have to do really is change this point here, okay, which will be something like G01. You can very easily find it that it's just this value here, which at this new temperature is not 4.8, but it's minus 16, okay, 0.3. And therefore, kilojoules. Remember, it's times 1 mole, so it's not kilojoules per mole, clearly. So you see that now, essentially, the new value of this difference here is the new value of dg0, okay, which is now negative, okay? In this case, it was positive, okay? So now the shape of our G psi has changed, and now the value of equilibrium has shifted, you see, from here to here. So essentially changing the temperature has changed the conformation of this graph, essentially because we're taking this and shifting it down here, okay? So you see essentially that this delta G, okay, has a very important role, the difference between the unmixed reactants and unmixed products, okay, in Gibbs energy, has a very distinct role in whether the equilibrium is shifted more towards the right, as in this case, or towards the left. In fact, you can conclude that if, and this is the final thing I'm going to do. Sorry that I stole 5 minutes, but we had lost them. So if delta G generally is bigger than 0, the reaction generally favors products. And this is this case here. This delta G is 0, so you have the minimum, which is more shifted towards the, why do it's unbelievable how I always say the opposite. You have to excuse me, but there's something wrong with these words. Favors reactants. Okay, So it's more shifted towards the left. This is this case here. On the other hand, okay, if it's negative, like in this case, you see the reaction, the equilibrium point shifts more towards the right, and so the reaction favors products. And we will prove this more rigorously when we talk about, again, the equilibrium constant, okay? Okay, I stole enough time, so I'll end it here.